So in the last session, we had a quick discussion on the notion of normed linear space. Let us quickly recall the definition and move on. Assume you have a vector space over the field of real numbers or complex numbers. So you have facility to add vectors, you have facility to scale a vector. That's what you have in vector space. Now we want to talk about length of a vector. Suppose this symbol, which is read as norm, is a function defined on the vector space X, taking each vector in the vector space to a real number. So you are quantifying each vector in the vector space. It's a function satisfying following conditions. These conditions are modeled by looking at examples of vector spaces in R2, R3 and so on, R2, R3, etc., where you have length of a vector. Norm of X should be greater than or equal to 0. Length of a vector in vector space becomes 0 if and only if that vector is 0 vector in that vector space. Now I should say how length act with two operations available in the vector space. The length of scaled vector alpha x would be equal to length of x scaled by quantity mod alpha. And this is true for all alpha in K and X in X. And we should also have a nice interaction between the length function and the addition available to us. Norm of X plus Y less than or equal to norm X plus norm Y for all X and Y element of X. Such a function is called a norm. Then the function denoted by this symbol is called a norm. And once you have a norm on the vector space that you have started with, the pair is called a normed linear space. One reason for interest in normed linear space is that the underlying set is a vector space, so you can use all the knowledge that you have from linear algebra. Further, the norm, the length that you have defined just now, will give rise to a metric. And therefore, you can talk about concept from analysis like convergence, closed sets, open set, completeness, connectedness, compactness, etc., etc. Thus, this is a place where, as I told in the last lecture, linear algebra and analysis meets. Okay, but our purpose is very limited. I just wanted to give you a class of examples of a normed linear space arising from the theory of measure and Lebesgue integration. So with that goal, let us set our stage. So I have to start with a measure space. Consider a measure space. As you know, a measure space is a triplet. A set, a sigma algebra, and a measure. If you don't like it, you take X to be R, the set of reals, A to be the collection of all Lebesgue measurable subsets of R, and mu to be the Lebesgue measure F. Okay. But we can do it in a general setting. Let us begin by recalling that whenever you have two functions, let us say f and g, almost everywhere, then they yield the same integral value. F equal to g almost everywhere gives you that integral of f is same as integral of g. Yes or no?
Yes, sir.
Therefore, from the point of view of integration, there is no reason to distinguish two functions f and g if they are almost everywhere. Whenever they are almost everywhere, we can treat them as same in the integration theory. Okay, so let us start by noting it down. Recall that two functions need not be equal everywhere on x. Two functions on x that are equal almost everywhere on x yields same integral, assuming integrability and so on, yields same integral, and hence in point of view of integration, we can treat them alike. We can treat two functions that are equal almost everywhere to be the same. They are not same in the sense of equality of functions, but they are same as far as integration theory is concerned. In other words, suppose f and g are two functions defined on the measure space X that is given to you, real or complex. We may write and we may treat f and g as the same, and I declare like this: f is equivalent to g if f is equal to g almost everywhere on x. Once the two functions are equal almost everywhere, I will treat them equal in quotes. I put the symbol tilde, equivalent you can say. Okay, so this is my declaration. Two functions are equal if they are equal almost everywhere. Okay, so we declare like this. In other words, we don't have any reason to distinguish two functions if they are equal almost everywhere as far as integration theory is concerned. So now let us look at this collection. Look at, let us say script f is equal to collection of all functions, real or complex valued functions defined on X, where X is the ambient space in your measure space, and F is measurable. I should say, to be more precise, mu measurable. Measurability is with respect to the measure that you have defined on sigma algebra of X. Okay. And yesterday you have seen what is the meaning of function is measurable. You take an open set in the codomain, because the codomain is a topological space here. You can take an open set in the codomain and demand that its inverse image is measurable. So that's the definition of mu measurable function. Okay. And you can see that the tilde that I have introduced before, F is related to G if F is equal to G almost everywhere on X, turns out to be an equivalence relation on this set. Then tilde is an equivalence relation on script F. That is obvious. Any function is related to itself under the relation that I have defined. If you want F is related to F, what you want is that F equal to F almost everywhere. Is that true?
Yes, sir.
In fact, F is equal to F everywhere on X, right? Now, if F is equal to G almost everywhere, then G is equal to F almost everywhere. Only thing slightly non-trivial is transitivity. If F is equal to G almost everywhere and G is equal to H almost everywhere, what is the meaning? F equal to G almost everywhere means you can throw away a set of measure 0 and except on that set, F is equal to G. From X, you can throw away a set A of measure 0 and excluding that set, F is equal to G on X. Do you follow?
Yes, sir.
Similarly, G is equal to H almost everywhere means you can throw away a set, need not be the same set, say B, so that G is equal to H except on H, except on the set B, where B is of measure 0. Okay. Now I want F is equal to H. You have to throw, which set you have to throw? Yes. Yeah. So you are done. So therefore, F equal to G almost everywhere, G equal to H almost everywhere will imply F equal to H almost everywhere. In short, the relation that you have defined is an equivalence relation. Now comes the routine things. Once you have an equivalence relation, what can you talk about? You can talk about equivalence classes, and equivalence classes form a partition and so on. Okay. For F in script F, let the equivalence class of F be denoted by bracket F. This is the usual notation we use. And what is by definition bracket F? Bracket F is equal to collection of all G from X to K. You have defined the relation on F. G is mu measurable and G is related to F. This is what the equivalence relation means. Equivalence class means G is related to F means G is equal to F almost everywhere on X. So this is, you consider all such G and collect inside a basket and that basket is denoted by square bracket F. Okay. Now, what does it mean? Essentially, what we are doing is, instead of dealing with a single F, we are going to deal with bracket F, which is in fact a collection of function. But what is to be noted that you take any element in bracket F, let us say G and H in bracket F. Do you see that integral of G will be same as integral of H?
Yes, sir.
That is because G and H are all almost everywhere equal to F. So any element in bracket F will give you the same value to the integral. Okay. In other words, we are identifying the function F with bracket F because as far as integration is concerned, I don't mind whether I have to take F or I have to take an arbitrary element in bracket F. Doesn't matter. Both will give you same answer. Is that okay?
Yes, sir.
Now also recall that equivalence classes are either disjoint if they have a common element, then they should be exactly equal, are either disjoint or identical. So what you do is you collect all distinct equivalence classes. Consider the collection of all equivalence classes. Not all, but let us say distinct equivalence classes. Okay, that collection I will denote by, and in fact, this is called quotient space. This is the quotient space. This is a routine thing in mathematics. Whenever you define equivalence relation, you can have equivalence classes, you can collect distance equivalence classes, and that is called quotient space. And it is denoted by F quotiented with the relation. This is the usual notation we use. Okay. So we have identified the distinct equivalence classes. Okay. And if you take one equivalence class, any element in that equivalence class will yield you same integral value. Okay. So now onwards, so it is like grouping. We grouped elements together which have same taste. Here the same taste means same integral. So we are just grouping. Instead of looking into, let us say, 63 students in your class, I first wanted to group you people according to some common characteristics, so that instead of going and checking every 63 individual, it is enough to check this many classes. Okay, so this is what we are doing. So now onwards, whenever I say an F, small f in F, what actually I mean is not small f, I mean bracket F, because I'm going for the integration theory. Okay, is that okay?
Yes, sir.
Now onwards, let
Yes.
me even write it in, put it in writing. Now onwards, when we say F is in F, a single function is in F, instead of F, you can take any element in square bracket F. We really don't mean a particular F, but the entire class. And that F is taken only as a representative of the equivalent class. Okay, so we are treating F as a representative of script f. Square bracket f. Okay, so this is the agreement that we make. Now, we say that I'm going to define a new set. We say that f element of f. Keep in mind, when I say f, I actually mean any f equivalent to f. Any g equivalent to f. Or in other words, I mean square bracket f. We say that f in f is in, I'm going to define a new set. Okay, the notation is this: LP x a mu if I declare that a function is in this new set if integral over x mod f power p d mu is finite. In other words, pth power of mod f is Lebesgue integrable. Okay. So, and I consider all such functions, and that set is LPXA mu. Okay. So, is the set clear? What is LPXA mu? It is collection of all Lebesgue measurable function whose pth power of the modulus is integrable. Is it okay?
Yes.
And I should say what is P, where I was silent about P, where P is some real number with this property. 1 is less than, P is less than infinity. So fix P and you collect all those functions whose pth power of the modulus is Lebesgue integrable. Okay. Now let us note certain things about this collection. Suppose I pick two functions f and g in this LP x a mu. Okay. Now f is a function from x to k, g is a function from x to k. So do you agree that modulus of f of x and modulus of g of x are going to be real number? Then we are not considering extended real value. Remember, f is a function from x to k, and k is either r or c. Okay. Therefore, mod fx, mod gx are real numbers for each x in x. Okay. Now let us define m of x is equal to maximum of these two things. For two real numbers, you can find the maximum. Now note that for each x in x, modulus of f of x plus g of x by triangle inequality of a real or complex number, it is less than or equal to mod fx plus mod gx. Okay. And this is less than or equal to mx plus mx. So 2mx. So for each x in x, modulus of f of x plus g of x is less than or equal to 2 times m of x. And consequently, modulus of f of x plus g of x whole power p is less than or equal to 2 power p mx the whole power p. Simple calculations. Do you agree? Yes or no?
Yes.
Yes.
Now, look at mx. Do you see that mx will be either mod f of x or it will be mod g of x, depending upon whether mod f of x is greater than mod g of x or vice versa. So for each fixed x, m of x is going to be either mod fx or it is going to be mod gx. Agree?
Yes, sir.
So anyway, m of x will be less than or equal to mod fx plus mod gx. For each x in S, m of x is equal to modulus of f of x or modulus of g of x. Okay. Or m of x power p is equal to modulus of f of x power p or modulus of g of x power p. And therefore, m of x the whole power p is less than or equal to mod f of x the whole power p plus mod g of x the whole power p. I am adding an extra quantity. So this is true for every x. Agree?
Yes, sir.
Therefore, modulus of f of x plus g of x the whole power p, this let me call 1, this let me call 2. You amalgamate 1 and 2. You combine 1 and 2. This is less than or equal to 2 power p mx power p. I would write as modulus of f of x the whole power p plus modulus of g of x the whole power p. Okay. So now it is of the form you have some function alpha x in the left side and beta x in the right side. Both are non-negative and alpha x is less than or equal to beta x. Therefore, that implies integral modulus of f of x plus g of x the whole power p t mu is less than or equal to 2 power p integral over x mod f of x the whole power p d mu plus 2 power p integral over x modulus of g of x the whole power p d mu. And we started with f and g in LP. Look at the definition of LP. A function is in LP if integral over x mod f of power p d mu is finite. Okay. Therefore, since f and g are in LP, you will get integral of mod f power p d mu is finite. Integral over x mod g power p is also finite. And that will give you that integral over x mod f plus g the whole power p d mu is finite. Okay. Thus, integral over x mod fx plus gx the whole power p d mu is finite. Because you started with f and g in L mu. And what it gives? For an element to be in LP, you need that the pth power integral with the modulus is finite. Okay. So now you decipher this. So what's your conclusion? That implies what? Can you tell me?
fx plus gx belongs to
That is f plus g, right? F plus g is as a function is in LP. Okay. X a mu. Okay. For simplicity, we shall just write LP mu. We can forget about x and a LP mu. That's notation, another notation. So f plus g is in LP mu. So whenever f and g are in LP mu, f plus g is in LP mu. Okay. Now, look at f is in LP mu and alpha be a scalar. Okay. And you can look at integral over x modulus of alpha x the whole power p d mu, which is equal to integral over x mod alpha power p mod f of x the whole power p d mu. Okay. Alpha is a constant, you can pull it out. Integral over x mod f of x the whole power p d mu. And once f is in LP, this integral, the pth power integral will be finite. And therefore, this is less than plus infinity. A finite quantity times a real number mod alpha power p. So this is going to be finite. And that implies, therefore, alpha f is also in LP mu. So what is the message? What is the takeaway message? When f and g are in LP, f plus g is also in LP and alpha f is in LP. So what's the conclusion that you can make?
LP is a vector space.
Thus, LP is a vector space. Consequently, you should treat LP inside collection of all function. But already you know that collection of functions is a vector space with the usual operation. So this will become a subspace. Now forget about collection of function. This itself is a vector space. Okay. Consequently, actually we have to verify all other property. But if you take LP mu is a part of the already known vector space, these two is enough. Consequently, LP mu is a vector space. And now go back to normal linear space. The basic ingredient for a normal linear space is a vector space. So I have a vector space now. Okay. So what will be my next interest then? Automatically. Can you guess?
Define a norm.
Define a norm on it. So somehow I want to talk about lengths of elements in LP. Okay. So that's my next goal. So in fact, there can be some relation between LP and LQ and so on. So let me skip for the time being and let us go to definition of norm. I'm just thinking, since available time is limited, what I can skip. Okay, anyway, let us define no. Now, for each F belong to LP mu, but remember we already had an agreement. Whenever I talk about F in LP mu, actually I mean the equivalence class of the function. Define norm FP is equal to integral over x modulus of f of x the whole power p d mu the whole power 1 by p. P is a fixed real number. You have already defined LP mu, and on LP mu, I am defining this quantity. And my next aim is to say that this defines in fact a norm on LP. For that, I have to see that the four conditions are satisfied, out of which only non-trivial condition is the triangle inequality. For instance, do you see from the very definition that norm of F, right now it is not a norm, but I have to read something, so that double line I am calling it as a norm. Norm of F suffix P is greater than or equal to 0. Do you agree?
Yes, sir.
How does it follow? Because you are
Integral
integrating a
mod.
mod.
Non-negative.
Okay. Yeah. Now suppose we have. Now suppose the norm is 0. Norm f suffix p is 0. What does it imply? That implies that the integral is 0. And if the integral is 0, what is your conclusion?
Function is 0 almost everywhere.
Almost everywhere. So I can say that this implies f is equal to 0 almost everywhere on x. But already we have identified two functions that are equal almost everywhere, right? With that equivalence relation. So once f is equal to 0 almost everywhere, with the identification we have in mind, f is equal to 0. Okay, that implies f is equal to 0 with the identification we have. Similarly for the reverse. Okay, and it is easy to see that norm of alpha fp is equal to mod alpha times norm fp. This is also easy to see. Only non-trivial thing is triangle inequality. That's not that easy to see. And in order to establish triangle inequality, we have the so-called Minkowski's inequality. Okay, so this I will not prove, but I will just state Minkowski's inequality. And what Minkowski's inequality state is the following. For f comma g in LP mu integral over omega modulus of f of x plus g of x the whole power p d mu the whole power 1 by p is less than or equal to, unfortunately I don't have time to establish this inequality, modulus of f of x the whole power p d mu the whole power 1 by p plus integral over omega modulus of g of x whole power p d mu the whole power 1 by p. It is not trivial. This is a non-trivial result called Minkowski's inequality. If you want to prove Minkowski's inequality, first I have to establish what is so-called Helder's inequality. Follows from Helder's inequality. Written Holder, but pronounced as Helder. And all these things, Helders and so on, can be derived from the arithmetic geometric mean inequality. And arithmetic geometric mean inequality can be derived from a simple fact that whenever x is a real number, x square is greater than or equal to 0. So it is very interesting to see with a trivial thing, x element of R implies x square greater than or equal to 0. You can go to AMGM inequality, arithmetic mean geometric mean inequality. From there, you can go up to Minkowski's inequality in a sequential way. So I don't have time to do that. So let us accept this Minkowski's inequality and keep that in mind that is proof is non-trivial and it follows from Helder's inequality. That much is enough. Now look at Minkowski's inequality. What it exactly tells you. What is the left hand side? Is that norm of f plus g suffix p that we defined? Look at the definition. Where is it? Yeah, this was our definition of norm. Let me highlight here. Okay, keep this definition in mind and look at the left hand side of Minkowski's inequality. What do you see?
Norm of f plus g.
Norm of f plus g less than or equal to, and what is right hand side? Norm f plus norm g, right? So note that Minkowski's inequality translates to norm of f plus g p is less than or equal to norm f p plus norm gp. Okay. Thus, the norm that you have defined like this is in fact a norm. Thus, the quantity that you have defined, norm suffix p, is a norm. Norm on which vector space? On LP mu. LP mu was a notation we simplified for LPX A mu. In other words, LP turns out to be a normed linear space. Thus, for 1 less than p less than infinity, LP mu is a normed linear space. with the norm, with the norm defined by, this is the takeaway message, okay, defined by this quantity, integral over x mod f p d mu the whole power 1 by p. So this is the takeaway message. So now you have an example of normed linear space coming out of integration theory. In fact, not one example, you have a class of example. Remember, P is arbitrary, real number between 1 and infinity. So you have uncountable family of L1 mu, you can, for instance, L2 mu, L3 by 2 mu, whatever it is, L root 2 mu, what not. So you can have all type of spaces, Lebesgue spaces, which gives you examples of normed linear space. Is that okay? Yes or no?
Yes, sir. Yes, sir.
One thing that you should keep in mind that when I talk about a function f in LP, actually I don't mean a function, I mean a collection of functions. Or when I say f in LP, actually I don't mean an f, but I mean an equivalence class of f. That point is to be stressed. So we say that the Lebesgue, this is called Lebesgue spaces. Let me, Lebesgue spaces. Whenever I say Lebesgue spaces and I say take an element f in Lebesgue spaces, f is actually not a function, but f is a class of functions. Why? Because if you want to talk about a norm, norm fp equal to 0 should imply f is equal to 0. But you will not get f equal to 0. You will only get f is equal to 0 almost everywhere. So functions are determined only up to almost everywhere. Do you understand?
Yes, sir.
That is why, strictly speaking, that each element is not a function. Each element is an equivalence class. And you note that inside an equivalence class, I identify all functions that are almost everywhere equal. G is equivalent to F. That means G is equal to F almost everywhere. So I don't distinguish between two functions that are almost everywhere equal. So F is equal to 0 almost everywhere is enough to say that F is equal to 0 as far as this equivalence relation is concerned. Okay, but it is a common abuse of language to say that an element in Lebesgue space is a function. You take a function f in LP. Actually, you are not taking a function, you are taking an equivalence class of functions. Okay. Is that point clear?
Yes, sir.
Now, I have missed a few real numbers. P, I am taking from 1 to infinity. 1 excluded. Why 1 is to be excluded? Why not I take y p equal to 1? Okay. Now let us consider, because that's more easy. That's why I avoided first. Now let us consider L1 mu. What is L1 mu? It consists of all functions. When I say functions, actually equivalence classes of function, such that integral over x mod f dm is finite with the norm. Now I don't know whether it is a norm, so I will put it inside a quote. Norm defined like norm f1. This is the definition. Integral over mod f d. P is equal to 1. That's it. Now in this case, to see that norm is a norm P is a norm, only non-trivial thing was triangle inequality. And for triangle inequality establishing, we use the what is called as Minkowski's inequality. But in this case, you don't need Minkowski's inequality or anything. Triangle inequality will be straightforward. Let us see. Let f comma g is in L1 mu. Then norm of f plus g1 will be equal to, by definition, integral over x f plus g d mu. If you want, you can put f of x and g of x. But note that modulus of f of x plus g of x is less than or equal to modulus of f of x plus modulus of g of x. Therefore, integral of this left hand side function is less than or equal to integral of the right hand side function. Therefore, norm of f plus g1, which by definition is integral over x f of x plus g of x d mu, is less than or equal to integral over x mod f of x d mu plus integral over x mod g of x d mu. Okay, and first one is what you have as norm f1, and second one is what you have as norm g1. So you have norm of f plus g1 is less than or equal to norm f1 plus norm g1, because in between you have a less than or equal to. Thus, norm of f plus g1 suffix 1 is less than or equal to norm 1 of f plus norm 1 of g. Other properties are easy to observe. Easy to observe. And therefore, L1 with norm 1 is an example of, is also a normed linear space. So clubbing LP with the norm P is a normed linear space for 1 less than or equal to P less than, strictly less than infinity. Thus, LP norm P. I'm not writing any bracket because that is understood. We have to start with a measure space. LP x a mu, I should write. Norm P is a normed linear space for 1 less than or equal to P strictly less than infinity. So far so good. So what we achieved is only one nice example of a normed linear space that is coming out of measure theoretical concept. Okay, and that is usually called as Lebesgue spaces. So far so good.
Yes, sir.
Yes, sir.
Now I will
Yes, sir.
adjoin one thing and stop, namely, let us see what happens if P is equal to infinity. Obviously, when P is equal to infinity, even the definition of LP, look at the definition of LP that we had. I'm not talking about the definition of norm, definition of LP. How do you define LP? Here, integral over x mod f power p d mu is finite. So you cannot talk about integral over x mod f power infinity d mu is finite. So definitely, if I want to include p equal to infinity, I cannot use this definition. Is that clear?
Yes, sir.
So how do I modify the definition is the question. Okay, so yeah, I have 10 minutes. Let us start with the bounded functions that you know. Let x be any set. Let x be any set. And suppose f from x to k, k is real or complex, is a bounded function. It's a bounded function. You know the meaning of bounded function. Means that is there exists a positive constant m such that modulus of f of x is less than or equal to m for all x in x. So this is the definition of bounded function. Okay. And once you have a bounded function, since f is bounded, we can talk about the supremum of modulus of f of x in x. Is that okay? A well-known fact.
Yes.
Now, let us collect all bounded function inside a basket. Let p script b x comma k be the collection of all bounded k valued function. K is real or complex. So real or complex valued functions defined on same set x. X need to be only a set. Now, suppose you have two functions f and g in B. Then f is bounded, g is bounded. Do you see that f plus g is bounded?
Yes, sir.
Do you see that alpha times f is bounded?
Yes, sir.
So essentially what I am saying is, therefore this collection that I just now formed is a
Vector space.
vector space. In fact, P, X, K is a linear space. As you know, once I have a linear space, I am interested to see whether I can quantify vectors in it, whether I can talk about length. Okay. For that, for each f in B, xk, define, I'm going to define a norm. Okay. Norm of f is equal to, I already told, you can talk about supremum. That supremum I am taking. Supremum x in x modulus of f of x. This is my definition for norm f, usually denoted as norm suffix infinity. Okay, and called as supnorm. You can see that it turns out that it's easy to verify all the four conditions. It turns out that norm suffix infinity is a norm on bxk called supremum norm or infinity norm. So far so good. This is nothing connected with measure theory. This is just classical analysis and linear algebra. I collect all functions that are bounded on defined on same set, that I have noted that it is a vector space. Now I defined a norm on it by looking at supremum. So far so good.
Yes, sir.
Now what I do is, instead of starting with a set, let us say that we have a measure space. Now suppose X. So in this process, I have given you one more example of a normal linear space, namely bxk. It is not coming from measure theory, but still it is an example. Okay. Now this bxk, look at bxk, that will motivate our next example. Now suppose x a mu be a measure space. Now I can talk about measure, etc., not just set, and f be a function from x to k, not from set. It is now from a measure space. Okay. How did you define boundedness? You define boundedness like this. modulus of f of x is less than or equal to m for every x less than element of x. But now since I am in a measure space, I don't mind if this condition is violated on a set of finite measure. I don't mind. I repeat, I don't want the condition to be true for all x. I am okay even if the condition is violated, but the violated set should be of measure 0. Is that make sense?
Yes, sir.
And such functions are called essentially bounded. Okay. We say f is essentially bounded. We say f is essentially bounded if there exists m greater than 0 such that modulus of f of x is less than or equal to m, not for all x, almost everywhere on capital X. So where it is violated is of measure 0. Is that okay? Because measure 0 set are irrelevant to me as far as integration is concerned, or as far as measure theory is concerned. Is that okay?
Yes, sir.
So this is
Yes,
a new definition, namely essentially bounded. A function is essentially bounded if it is bounded except on a set of finite measure, zero measure, except on a set of 0 measure. Let me quickly give an example. Let us take x is equal to 0, 1. Open interval 0, 1. And f of x is this. X if x is irrational. And let us say 2x if x is rational. I mean irrational and rational in x. Now x I am endowing with our usual Lebesgue measure. Okay. Now with the Lebesgue measure. Is your fx bounded? The values are x and 2x, real, rational and irrational accordingly. But anyway, it is everything is inside 0, 1. Is fx bounded?
Yes, sir.
What is the bound? Note that modulus of f of x is less than or equal to 2 for all x in 0, 1. Do you agree?
Yes, sir.
Yes.
And in fact, this I will leave to you. In fact, the supremum of f, that is supremum of modulus of f of x, x belong to 0, 1. That will also be 2 because you can go as close to 2 as you want. You have a 2x. You have a 2x when x is rational. So you can take a rational near to 1 and you can go up to 2x. Okay, so that's why since you can go as close to 2 as you want, you will get that supremum is 2. Okay, now when you talk about essentially bounded, you can throw away sets of measure 0. Please recall that the set of rationals is of measure 0. Yes or no?
Yes, sir.
So now what I will do is, let us see, let us consider 0, 1. Okay. And let us say that we are throwing away all rational number after 3 by 4. Okay. We are throwing away this. Not entirely, only the rational number. Q in 3 by 4 thrown away. Doesn't matter because what I thrown away is of measure 0. Now you tell me, can I say modulus of f of x less than or equal to 2 times, I will get 3 by 2 almost everywhere on 0, 1. Is that correct?
Yes, sir.
Because I have thrown away all the rational numbers in 3 by 4, 1. So you have all rationals and irrational in 0, 3 by 4. And after 3 by 4, you have only irrational. and for irrational the value is x, and for rational the value is 2x. Okay, so it will be less than or equal to 3 by 2. Now instead of 3 by 4 1, suppose I am throwing out rationals from half to 1. Okay, q in half 1 is thrown out. Now can you tell me a bound for f of x? Modulus of f of x is less than or equal to
1.
1. Almost everywhere on 0, 1. So you can say modulus of f of x is less than or equal to 3 by 2 almost everywhere. You can say modulus of f of x is 1 almost everywhere on 0, 1. And maybe if I take not 3 by 4 to 1, but say 0.9 to 1, you may get a larger bound. Okay. However, I want to bound it as nicely as possible. So what I will do is look at set of all m such that modulus of f of x is less than or equal to m almost everywhere on x, and take infimum of them. This is the best I can do. Okay. Here I have mod f x less than or equal to 3 by 2 almost everywhere on x. Here I have mod f x is less than or equal to 1 almost everywhere, and you may get another bound also. But what is the nice bound I can get is the infimum. Do you agree?
Yes, sir.
And this has a name. This is called essential supremum of f. Not supremum of f, it is essential supremum of f, because you are talking about essentially bounded function. At the core, it is bounded. It is not bounded when you just look, but except on a finite measure, it is bounded. So at the core, essentially, it is bounded. And you consider the best bound, and that is called the essential supremum instead of supremum in the old version. In the old version, it was everywhere bounded, and you are talking about supremum. Here it is essential supremum. Is that okay?
Yes, sir.
And now I am going to denote it. Consider, I am stopping with this. L infinity mu, what is that? Okay, is equal to collection. I will write in notation. LP mu I have already discussed for 1 less than or equal to p less than infinity. Now for infinity, my definition is this. Consider all functions f from x to k, where x is a measure space, where f is essentially bounded. F is essentially bounded. Set of all essentially bounded function. You can see that L infinity mu is a vector space. Is a vector space. Okay. Once I have a vector space, I would like to define a norm on it. For each f in L infinity mu, when I say f, I actually mean f with no distinction between f and g whenever f and g are almost everywhere equal. Anyway, for each f in L infinity mu, I want to define norm f infinity. This is the notation. Okay. Can you guess what will be the definition? F is essentially bounded. Therefore, there exists an m such that mod fx is less than or equal to m almost everywhere. I want to find nice bound. So I have to talk about the infimum. So what will be the definition of norm f infinity? Any idea?
Essential
Essential
supremum.
supremum.
Essential supremum of f. That's the. And you can see that norm satisfies this norm that I have defined is a norm on all the condition, norm on L infinity mu. And therefore L infinity mu with this norm is also a vector space. Is also a vector space. Sorry, normed linear space. Let me avoid also because I am specific about infinity is a normed linear space. So now you can club. Thus, what you have is LP X A mu along with the norm P is a normed linear space for 1 less than or equal to P less than or equal to infinity, and these spaces are called Lebesgue spaces. But keep in mind that for P equal to infinity, the definition of LP and definition of norm both are different. It is not with other P. How L infinity is defined, it is collection of all essentially bounded function. And how norm infinity is defined, it is essential supremum of F. But for other P's, the definition goes like the Pth integral is finite. That's the definition of LP, and norm is defined as this quantity, whatever this one. Okay, so the takeaway message is that the capital LP spaces that we have defined constitutes wonderful example. Why wonderful? You will see in function analysis. They are wonderful examples of normed linear space. With this, I stop. Now you will study more properties of LP. Once you have a normed linear space, in particular, it is a metric space. So you can ask questions like, is it complete? Okay, and you can see that LP spaces are complete for every P, 1 less than or equal to P less than or equal to infinity. And you can ask questions like, why don't you go for P between 0 and 1? I have started only from 1. Okay, that question. Why not P to be negative and so on? Negative may be more clear, but why P less than 1? Okay, those questions will be answered possibly in your course, function analysis. So with this, let me stop this lecture and also the course. And I wish you all the very best. With whatever available time, I hope I have done